Good morning, good afternoon, good evening to everybody on whoever is watching this Friday talk show with Global Electronics. And this is your host Rajiv Kulkarni, once again bringing you this interesting talk show of today's this week's, I would say. And good morning, good afternoon, good evening, because we don't know which part of the world you're watching the show is. And so, with that said, welcome to the show, and thank you very much for supporting the show and supporting the channel as always. And as we discussed last week, we spoke about densification in the electronics manufacturing, and we did speak part one of that up to the printed circuit boards. And then today we are going to continue the part two of it, which would be more on the advanced packaging and the components and so on and so forth. Densification is definitely a very interesting subject because what it means in electronics is the process of increasing the density of components and circuits or systems on a given surface area or the volume. This is driven by the need for smaller and lighter and more powerful electronic devices. Yes, as we all know, the electronics gadgets, electronics requirement is increasing every day, and the need of high density electronic circuits is going more and more on the higher side because of the technology which is driven by AI, which is driven by telecommunication, which is driven by more and more data, centers. I would say data center means very powerful data center. So the need of electronics is going up. And even in the automotive sector, if you look at, we need very smart electronics. As we know, there are like tons of electronics in the automotive sector, and so does in the medical and aerospace and other sectors that we deal with on a day-to-day basis. With that said, today also we have Mr. Ambaprasad, who is a technical guru, technical expert, and who is a IPC trainer, and as well as he is the current Surface Mount Technology Association India chapter president. Mr. Ambaprasad lives in Bengaluru, that is the city of Silicon Valley of India, and which is supposedly the technology hub for various technical aspects of our industry. Let's welcome Mr. Ambaprasad and to join us, and let's have this discussion and on the densification in the electronics. Welcome to the show, Mr. Amba. How are you doing this evening?
Yeah. I'm doing very good. When you talk of Bengaluru today, also there was a news that the AI boom is going to increase a lot of jobs in Bengaluru or Bangalore, the way the world people call it. In fact, there is a term in US and Europe, the subcontract things to third world countries. It is called as you are Bengaluring a job. So Bangalore is a phenomenon by itself, actually.
Okay, great. So, thank you for joining the show today. As we all know that you are a busy individual and taking some time and sharing the wealth of the knowledge with our audience, with our electronics community. We thank you very much for that. So I'm going to share the screen here, and I hope, are you able to see my screen?
Not yet.
Not yet. Okay, I'm going to share the screen. Okay, I think you should be able to now.
Go to full size mode. That arrow.
Yeah. Can you see the screen right now?
I can see the screen now.
Okay, just hold on one second.
Expand arrow, the diagonal arrow on the top.
Yeah. Don't worry. I'm going to fix that.
Yeah, that one. Yeah, that's it.
Okay.
Yep.
Okay, here you go. And Amba, the floor is yours.
Yeah, Uh, okay, nice that you told a floor because when we do a placement in electronics, it is called as floor planning.
Yeah.
And the floor has got a lot of, there are floor shows also in Bengaluru, which go on in the weekends. So there are a lot of good things about the floor. So basically, we last week we covered Moore's law and its new interpretations, through-hole densification, component package, pin spacing roadmap, how it's are becoming denser and denser. And then we went up to through-hole technology densification. And in spite of surface mount technology and other technologies coming, people thought through-hole will die a slow and natural death, which didn't happen. So that's one thing which person should remember. Through-hole and these high densities, they exist together. And now can start with attribute-driven projections in chip packaging, which is slide number 10.
Yep.
Uh, I think one slide next. Yeah, go next. Yeah, that's okay. So basically, the ball grid array started in somewhere in 1996 by the then a very repeated risk versus CISC fighting was going on in packaging. There were two sides, two leading semiconductor companies for, I mean, you're divided. Either you're working with them or you're working with the other one. So they started a BGA and they started with 1.524 mil spacing, that is 60 mil spacing between the balls. The BGA balls have got one very good attribute. Even when you place the component, say, about some 10-20% offset with respect to the pad centers, due to reflowing and capillary action, they realign themselves. So that way, BGA became the go-to package by a lot of semiconductor companies. So 1.5 to 4, they cut off 20% in that. They reduced by 80%. It became 1.27 which is 50 mil. Then 1.27 they took and they again reduced to another 80%. It could have become 1.016 mil. So again, at that time, JEDEC came into picture and they said, let's talk only in millimeter, hard millimeter, but not in the mil numbers. So they came to 1 millimeter pitch. Now 1 millimeter pitch in around 1998 was state of the art, but now 1 millimeter is, it is the regular. I mean, you don't have to worry about it. It is as regular as a white shirt. I mean, everybody knows how to maintain it. Then it became zero point 0.8 mm. Then it became 0.65 millimeter. Then zero point 0.5 and zero point 0.4. Up to 0.5 mm, it can be assembled easily on a PCB. But once you go less than 0.4 mm, it cannot be no longer assembled using regular technologies. You have to do bumping or wire bonding or compression type of an assembly, thermocompression assembly. Soldering way is no longer possible. I can go to the next slide, please. Yeah, and in the meanwhile, since the ball pitch was reducing, the bump pitch, and again the lot of these drivers and transistors and diodes which are used for protection and other stuff, they started reducing the pitch, and they coexist. I mean, in any circuit, you cannot do a circuit with ICs alone. You require a lot of these supporting components. Some of them are active, some of them are passive. So they also started shrinking. So I think up to zero point 0.5 millimeter pitch, now we are looking at a zero point 0.5 millimeter, 0.3 millimeter, 0.6 millimeter in the screen. If you get into 0.3 millimeter, you enter an arena, what is called as high density packaging. The regular PCB technologies will not apply. Okay,
Mm.
next slide, please. Yeah. So if your trace width and spacing is less than 50 micron, that is 2 mil, and micro wire diameter is less than or equal to 75 microns, and the dielectric thickness between the two layers is about again two mils, 50 microns. So the shrink is not only happening in X and Y direction, the densification is happening in the vertical direction also. So here you go called as ultra HDI or semiconductor like packaging. So the PCB design rules will no longer apply. The designers and the PCB fabricators and assemblers should think and act like a semiconductor company. So then only it works. Yeah, that's it. So this was the roadmap given by IPC. They gave a scenario, the inflection points. You see line space, the industry started with, if you go on the y-axis here, 100 by 100 spacing, microns, which is 4 mil space and 4 mil gap, which is a regular PCB. Then they went for 75 by 75 microns. Then they hit 50 by 50 microns, they go to ultra HDI. Before that, it is called as either HDI or PCB. But below that, it is called as ultra HDI. And again, the BGA pitch, 800 micron, 500 micron, 400 micron, 350 micron. That is the inflection point. Once you reach there, you're not no longer designing a PCB. You are designing a semiconductor substrate instead of a packaging. That's how it goes. Yeah, this is again the spacing and all projection given by SEMI. They projected the line space 2 micron by 2 micron by 2023. By 24, they're hitting 1.5 by 1.5. And then via pad size almost 17 micron. Via diameter 18 micron. And then flip chip pitch 35 micron. 35 micron. Rajiv, you think of 35 micron. The thickness of
Yeah,
copper is 35 micron.
yeah.
Okay. And a regular PCB, thickness of copper is 35 micron. Now your pad diameter is as thick as
The PCB
is
layer.
almost like a square. Yeah, that's what it
Yeah,
is.
yeah.
Then the interposer pitch, they're talking about 130 micron. That 130 micron is just to avoid electrochemical migration. And here, the negative, generally PCB is a negative process where you do etching and all. But when you hit this type of spacings, it has to be only an additive process. It's almost like a semiconductor.
Wow.
And these are roadmap even given by SEMI. They are going up to 2030. They are projected. But sometimes what happens, due to technology, what the project will happen in 2030 may happen in 2027 itself. So this is how the market demand people are ready to do. So that's where it is, and a lot of packages they are mentioned. But this is basically driven by IEEE heterogeneous integration. They do heterogeneous chiplets and all. Now, we told last week the scaling will not happen in silicon anymore. The scaling is happening in packaging. So this is the area where we are, and this is the most exciting time to be in the design industry and fabrication industry.
But the change is very fast as always. The design and also uh, the circuits, right? So
Yeah, see,
the
designers will not have a problem because your constraints manager, earlier you were setting in millimeter, now you have to set in microns. You have to act like a semiconductor company. Designers, they're very happy about densification. They can pack more and more things. The problem
yeah.
comes in noise. The problem comes in signal integrity and power integrity and in real packaging. Actually, all these PCB companies have to have clean rooms the way you do semiconductor packaging. And there is one more threat in this industry, which is called as machine-induced ESD. The assembly
Oh.
machine,
Uh-huh.
as long as there are two separate metals, there can be always a machine-induced ESD. the machines will get
Okay.
contaminated. So once they get contaminated, every packaging they do, it gets preloaded with ESD and comes. Actually, it is called as industry calls as JEDEC has got a lot of methods how to contain that and all. So that can be another topic by altogether that cannot be explained now. So your imagine you are purchasing a package, it is already preloaded with defects,
Correct.
especially electrostatic breakdown will happen. EOS, they call as EOS. So that's the EOS is the result of your electrostatic failure. This can be another topic together. It's not a problem. We can
Okay.
show. Yeah, and here in this roadmap, just go one back. We are showing IO speed is almost hitting 112 Gbps, and the fab nodes are less than 3 nanometers, the silicon.
Yeah.
And then IC package, the pitch we were talking about from 12 micron, and pin count are almost 50K pins are there in a package. That's what we are talking about. But the package the size remains the same. It is 50 millimeter by 50 millimeter. The BGA size cannot increase because I told last week, when you have a BGA, the first row and the second row and the last two rows, and first and second column and the last two columns, they are the business end of a BGA as far as high speed is concerned. That is called as a beach. People call as a beach front or whatever. All your high speed signals will either get terminated there or they start from there. Okay. So this is where we are, and substrate spacing is 5 micron by 5 micron. Line space is 2 micron by 2 micron. Bump count is more than 100. A layer count in the package, I'm talking about the package, can be 20 layer upwards. Yeah, that is where we are talking. This is a pure package which sits on the, these are all called as heterogeneous packages. They call it 2.5D, 2.75D, 3D, between 2 and 3D. That is the packaging technology. I think before this, we can take a break.
Okay.
Yeah.
Let's take. Welcome back to Global Electronics Friday Talk Show after the small break. And we have been talking about densification in the electronics manufacturing. And last week we had the session 1 of densification. And this week, that is today, we are having session 2, which is mainly focused on advanced packaging after the ultra high density PCB and HDI interconnect and so on and so forth, what Mr. Ambaprasad has been explaining us and giving a beautiful presentation. And I request all of you to please share our YouTube channel link with all your electronics colleagues, electronics friends. And if you are interested in coming on the show and talk about certain topic, you're more than welcome, and you can write to us, you can approach us, and we'll be happy to host you on our channel. And this is totally a pure service to the electronics community globally. And because I feel that we have to share the knowledge, wealth of knowledge that we have gained from our experience. And I think that's one way of giving back to the society that we have earned in so many years of our experience in the electronics manufacturing. In the electronics manufacturing, there are so many challenges, there are so many activities do happen on a day-to-day basis. And global electronics main, I would say the aim is to uh, address those challenges and talk to the engineers and discuss with the engineers, and they put these challenges or they discuss these knowledge based challenges or knowledge based information to the other our colleagues, our partners, and so on and so forth. So let's continue after break the second section of today's show, and I will start sharing the screen again, and so that we will continue where we left. Welcome back, Mr. Ambaprasad, after this small break.
Yeah,
And
we
you
can go
can,
for a full scale, full size.
yes. Just 1 second. So you can continue from where we left.
Yeah,
Yeah.
yeah, that's good. So second part of the second show. I mean, almost like a football, you know. They keep telling. Okay. So basically, Rajiv, I want to just make one correction to whatever you call the request, or you did a. In fact, we want people to tell us what they want to talk, and also we want the fraternity to tell us what they want to hear also. If they give us the ideas what technology or what part they want to hear, we can we can arrange for whichever talk they like. It can be
Those
one
talk shows,
one
yes,
day or
yes,
just talk shows.
yes.
Okay. And
Yeah.
here, so when we do simulation, earlier the people used to do simulation only for timing and signal integrity and all. Now, not now, even since last 10 years, people are doing multi-physics effects of densification. So what it means is, as things become closer and closer, let's say there are three parameters for a circuit to function. One is the electrical parameter, other is the mechanical behavior of the package and the PCB, yeah, or the ultra HDA, what we are talking about, and thermal. These three coexist. Suppose there is a electrical stress. There can be a mechanical misalignment in the multiple layers. Or if there is as things become hotter and hotter, these two interact and again they affect mechanical. There can be a shift in the placement, or there can be misalignment in layers. And if mechanically also, if it misaligns, this will induce electrical failure or thermal failure. These three will go together like a cycle. They keeps on going. They don't, this is the trifecta of multi-physics. What we do, there are a lot of other things in multi-physics. Even EMI, AMC, some people consider as multi-physics. But from what you call reliability perspective, I tell. So they generally people do simulation for IR drop, for a power simulation, crosstalk, signal integrity, signal delay in SI tools, and clock distribution is a science by itself. And then even given a choice, let's say I want to use a via of say a 5 micron by 5 micron. If I use even a via instead of 5 micron, if I use a via of 7 micron, I can bring a lot of reliability to the system. Okay. So I can, virtually, there is a lot of two things. One is you do state of the art, or you do, okay, little, I will go only 80% of the densification, and I have a 20% leg room for all this, that makes little sense. Better we don't go at the edge of the envelope, be little bit behind and do, then there will not be any reliability issues. This is one of a very conservative design approaches. Some people like it actually. They have it, it is in their company DNAs. You want to go, for example, you are telling your car can go at 140 kilometers per hour, but you still drive at 100 or 110. It is just to be on the safer side. So that's how
Yeah.
people solve. It is not over design. This is some sort of a sensible design. Yeah.
Okay.
Yeah, this slide is a very beautiful slide. In fact, this slide I picked up in aerospace industry. Yeah. So let's talk about just surface mount capacitors. For example, 0805, we are having 1206, 0603, 0402. In one 0402 package, you can put to four 0201 packages. That's how you achieved it. You take a 0402, cut it into four, x by 2 and y by 2, you get 40201. And again, 01 005, you can put four of them in 0201. It's like that, it goes on and on. You keep on folding it, you get numbers. But look at this. They have shown a very good picture. They started with a 1210 1210 capacitor. They have taken a few bottles, uh, some medical bottles. They have put in 10 pieces, they have put 12 1210. Then if you use 1206 design permitting, okay, you can put 25 pieces, almost two and a half times more densification roughly you are achieving. And you go to 0805, again 25 into two and a half, 65 pieces. And again you use O4, O2, 200 to 800, almost four times. And then 0201, if you use 3700 pieces from 800, almost four and a half times. And 01005, when compared to 0201, you are using almost 12,500 pieces, almost another four times, roughly. Uh, and then if you use 008, 004, you can put 1 lakh pieces. That is another eight times they are achieving. But
100,000
unfortunately,
pieces. Yeah.
yeah, this is how the JEDEC and all came into picture. And I told you earlier, there is a method in madness. So there is a physics and mathematics behind it. They have done it. Now EAA was driving it. Now JEDEC has taken over EAA. Now everything is JEDEC. So what happens is this has got in any design, wherever you have a power supply circuit and protection circuit, still people use 0805 or 1206. But in the same design, within another 2 millimeter gap, you'll be using one of these smaller packages like 01005, and they have to coexist. This is a very big challenge when you do the assembly. And even when you do design or when you do assembly, it's a very big challenge. You have to have a statistical process control.
Yeah.
Otherwise,
SPC.
just do. So here I'm just giving an example how, see, generally we knew when we do a placement file in a CAD perspective PCB, we generate XY data, the orientation and the center, and the component is placed. But when you go to uh, this kind of 0201 or 01005 components, you cannot place the way it is in the CAD data. You generate a CAD data and there is a solder paste has been applied. Okay. The solder paste has got a self-centering properties. It may have been misaligned also. Now you are aligning your component not to the pad in the PCB. You are aligning into the pad, you are aligning it with the solder paste. When you reflow, the solder paste, due to capillary action and self-centering properties, it drags the component and it aligns itself on the actual pad. So this is where your AOI inspection comes, and print and paste is no longer a screen. It can be a jet printed. And again, IPC, Connected Factory Initiative, if they find a failure at, say, printing, they immediately do the tuning, and it's a closed loop. So that is another subject by itself, and that's how it is done. Basically, if you do Ultra HDI, you have to use a SPC. Otherwise, it is not possible to just do the assembly. Yeah, that's what I just highlight on this.
Are we done?
Yeah, and next page. Yeah,
Yeah.
this is that is the last explanation. I have just captured this the strength, weakness, opportunity, and threat on densification. The concept of electronic component densification, the trend, yeah, it's there's a method in madness. It is a science by itself. Strength, space efficiency, X, Y, and Z direction, enhanced performance, higher density leads faster. So when we talk of electrical requirements, we talk of latency in telecom equipment, how fast you get the data or whatever it is. In fact, latency is required in automotive also, especially in brake control system. Okay, you want to brake, the information
No,
has
I
to reach
think
the brake system
uh,
as fast as possible. So latency not only comes in high-speed communication, latency comes in every electronics. It comes in automotive, it comes in aerospace, it comes everywhere. But yeah, the latency in telecom and AI, they are taken to a different level altogether. But latency applies in all electrical performance applies in all facts of life. So enhanced performance, innovation driver, encourages advancement in material and manufacturing. This is already happening. That's what. For example, we saw how the component packages have shrunk. Even material, people are coming with very good material. Weakness, thermal, enemy number one. And enemy, if you have 20 enemies in your electronics, enemy number 1 to 18 is thermal only. Then 18.1 is something else. Okay. Then complexity. The more intricate designs can complicate manufacturing and maintenance. Virtually, there is no repair. It is impossible. Yeah, it is just you have to remove the module and replace the module. So repair is impossible. And the cost. So when I say cost, there are two costs involved in electronic manufacturing. One is your non-recoverable establishment cost. So if you spend too much of non-recoverable establishment, you create your own packages, your BOM cost will come down. Or your BOM cost, if you want to be very costly, your NRSC you want to save, your BOM will become costlier. I'm not telling it is costlier by 10 times, but there is a balance between a BOM cost as an individual set of components or a purpose-built component. In a purpose-built component, you are buying only one component and you're paid already for the NRSC. Unless you produce in say 5,000, 10,000, 1 lakh numbers, you cannot amortize the cost, the engineering cost you have to recover. You have to produce in numbers.
correct.
That is when the
Correct.
cost is involved. Opportunity, IoT, IIoT. In fact, IIoT is used in connected factory environment. IIoT will help you how to improve assembly, but you require an advanced assembly to run IIoT. This is another closed loop. So higher density packages you require in IIoT. Sustainability, potential for reducing material usage and waste. Yeah, this is a very good opportunity. In fact, I told you what are the feature size will reduce, you use less and less material. And market growth, yeah, if one cannot do, the competition will do it. That's it. It is as
Yeah.
simple as the competition can be your neighboring company, or it can be your neighboring country or your neighboring continent also. It's a global electronics. So that's
Yeah.
what it is. Then threat, technical challenge, miniaturization, reliability issues, and competition have
Competition.
already told. So yeah, there is a very big opening for training and certification in densification for all industry bodies. We have taken a few names earlier, SMTA, INME, IPC, and they are all there. Sometimes they come together and do, or then sometimes they do individually. There are very good roadmaps are available. Even I have contributed quite a few roadmaps. So if people have any question, they can approach Global Electronics. We'll be more than happy to answer those questions. Thanks.
Absolutely. Absolutely, Mr. Amba. Thank you so very much. It was a beautiful presentation about the densification in electronics manufacturing in today's world, how the technology is evolving, from AI technology to high speed internet or high speed telecommunication, networking. Then we're talking about electric vehicles to the high-speed electric trains, and so the technology evolution is enormous, and it is growing at a lightning speed, I would say. And with that, the densification is becoming extremely important in the electronic circuits, because you need a very high speed intercommunication between the chips, between the circuits, so that the operation or the consumer who is using particular electronics gadget is in a position to operate in a very smoother way. Yes, we had a fantastic 2 sessions back to back on the densification. If you are not able to attend on a live show, you can always refer to our YouTube channel. It's always there, and you can go through all the presentation slides and so on and so forth. It is the presentation was given by Mr. Ambaprasad, who is a technical expert, technical guru based out in Silicon Valley of India, Bengaluru. That's in southern part of India, and he carries a very rich experience in the electronics design as well as manufacturing and electronics assembly. Thank you very much, Amba Prasad, once more, and thank you all the audience for watching the show today, and keep watching it and keep sharing our YouTube channel to your friends and your colleagues in your electronics industry, so more and more people can get benefit out of it. With that said, your friend, your RJ, your host, Mr. Raju Kulkarni, will take a leave for this week. I'll sign off this show today, and we will be back with yet another interesting talk show. Keep an eye on that. We will be sharing that information very soon with you, and next week, next Friday at the same time. Thank you all. Have a wonderful weekend, and God bless. Bye-bye now.